that the factorial of 0 is 1. And the factorial 1 is 1, just for fun. So one way to write this would be if n is less than or equal to 0, then 1, else n times the factorial of n minus 1, right?
Yeah.
Oh, sorry, this is wrong. I would say 1 here, for example. Okay, is that good? Everybody okay with that? Okay, so then instead we could wrap the whole this whole thing into an expression within a let expression. So instead we could say like factorial of n equals, and then we'll instead of calculating the n minus 1, we'll just call it n1 or something like that. So we would say let n1 equal n minus 1 in, and then we would say if n is less than or equal to 1, then 1, else n times fac of n1. And so I think this is what you're asking. So basically we just took what we had and we wrapped a let expression around it. And so then every time the recursive call is made, basically it passes a different value in for n, and then n1 gets calculated again from scratch. So every time this is called recursively, this is a brand new expression. Does that answer the question?
Yeah, so every time, like at the bottom when it calls fac n1, then the let n1 always will get updated to be like the next lowest value, I guess. So let always.
Yeah, so what happens is when we call this, it's like a brand new, it's a brand new like function call, right? So this gets called, and what this does is it passes n1 in for n. And so then basically this whole thing gets substituted for the body of the function where all the variables are updated. So you don't have to worry about any kind of collisions. It's really, the whole thing is done every time.
Okay, that makes sense. Thank you.
Can you do multiple variable declarations in a let statement?
Yeah. Well, this isn't a very good example, I guess, but
And so you could.
you would, but yeah, you can. So you would say like let x equals whatever, y equals whatever. You just, I think typically you would, the formatting or the style is to put them on separate lines.
Okay, and is it right that you can't tab over? Because maybe that's where I was getting an issue with. Like you have to do spaces.
Oh, for which part? Yeah, there's some rules for the variables, or?
Yeah, because I was trying to do like a let statement with multiple variables, but I think that my issue may have been that I was tabbing over instead of spacing, but I didn't know if you knew if that was a problem.
Yeah, it's a little bit like Python with respect to this. So,
Thanks.
Yeah. I try to avoid all that stuff because mostly what we're doing, we don't have to worry about it, but you do have to worry about with let, I guess, and where a little bit. Okay, any other questions? Okay. All right, so I'll just kind kind of briefly go through the exam 3. It'll be a little bit like exam 2, but it's going to be self-contained in Blackboard. So instead of a separate PDF file, the questions will just be inline in Blackboard. I think that'll make it easier for people to actually take. Also, it won't cover any questions from exam 2. So it'll only be stuff that's new that you haven't been tested on yet. And then just like the other 2 exams, it's worth 10% of your final grade. And then, like I said last time, the focus will be on Haskell. So the questions will just be related to Haskell. So some of the things that you should kind of refresh on or go back and study are just like the basics. So, you know, how expressions kind of work and bindings, what they mean. We talked a bunch about types. So these would be like the primitive types. Okay, slow down. Primitive types versus type classes. So a primitive type would be like int, and a type class would be num. And there's like kind of a relationship between them. So I just for using Haskell, you just have to have a basic understanding of this. Then we talked about lists and tuples. And so, for example, like lists are homogeneous, tuples are heterogeneous. Lists, the size of the list isn't like part of the definition of the list, but tuples, they are. And then how to talk about and infer or view the types. So like if I have a list of characters and the type is list char, etc. Then we talked about list functions, and we kind of went through a bunch of them. So there's like the operators cons and concatenation, and then head, tail. We talked about take and drop. We did last and then init, which is kind of the inverse of, or at the other end of head and tail. So last is like head, but it gives you the last element. Init is like tail, but it gives you everything but the last element. I think there might have been a couple more, I don't remember. I think we talked about reverse and length, for example. Oh, and null, that's another one. So with respect to list functions, you should have a sense for what these do, and then you should also be able to tell me what the type of these functions are. And we spent some time talking about function types. Okay, so you should understand that. We talked about conditionals. So if, then, else. We did some function definitions, and you did this on the homework assignments, and we've done this in the lecture. And then this includes recursion or recursive definitions, like factorial. And then the last thing we talked about last time was defining functions using patterns and guards, and so a couple of these topics, that's the homework assignment that's out now. And so probably in terms of the exam itself, it'll largely be kind of, a handful of shorter questions. And again, I'm going to design it so it's going to be about an hour, but then I'll give extra time just to get the answers in, get it formatted and stuff like that. And you'll have a week. So I'll put it out on Thursday and then after class, and then you'll have until the following Thursday to take it. And then just in terms of the class itself, so we'll have one more homework assignment, homework 10, and then we'll have the final. And the final is going to be during the final time, and it'll be a cumulative exam, but it'll be a Blackboard exam. And so the basic idea is I'll just be here, and you'll be taking it during that time, and then if you have questions and stuff, you can ask me. And it'll be kind of a mix of stuff from the exams. So, are there any questions? Does anyone have any questions? Is anybody even there? Alive?
We're alive. We're here.
Excellent.
Reading.
Okay, cool. All right, so I guess if there's no questions, then we'll just jump right in.
Wait, actually, did you say that we are going to be in the Zoom call during the final exam period? Like we all should be?
Yeah, well, so I don't want to drag things out for too long and stuff. And so I think for the final, the plan was we have a 2-hour block assigned to us for the final. And so I'll have an exam for you to take, like the Blackboard exam, like the ones like this third one and the other ones, but I'll make it self-contained. And so I'll set the exam so you'll have that full period to finish it during that time. And I'll be on Zoom so that as you're taking the exam, if you have questions, I can answer them. So like we're more like in a classroom setting for the final. As long as you take the exam and you do it during that time and you finish it, it's fine. If you don't want to use Zoom, that's totally fine. But if there are like clarifying questions that people have, then I'd like to be available to ask or to answer those questions for the exam.
All right, thank you.
And then, yeah, so I don't know, to me it's like, let's just get it over with and do it in that 2-hour block. And I'm sure everyone's got lots of other stuff that they're doing and need to get done. And so I think it's better maybe to do it that way than to just have it be like, do it whenever. So I'd like to do it that way. And I'm hoping to have the other exam graded, and I will definitely grade the quiz that was due today, and then you should have everything you need to really study for the exam, for the final. But for exam 3, again, there won't be anything from exam 2, so you don't need to spend time on that. Just focus on the things that we've done with respect to Haskell. And there's not even going to be any lambda calculus. That was on the exam 2. So for exam 3, it's really just the Haskell stuff we've talked about. And to study, I think it would be good to go back over the lecture notes, make sure you understand everything from the lecture notes, and then also the homework assignments we've done. Okay? All right. So today we're going to talk about how to define our own types in Haskell. And in my opinion, so like pattern matching and guards is super cool, but then the way you define types I think also is another place where Haskell and so like ML and Haskell and Camel and stuff really shine. So these functional languages really make it easy to define types, and then you can, there's not a lot of overhead. You can define types, and you can do kind of complicated stuff using the types. So one of the things about the types is when we're talking about user-defined types, is it's going to use a lot of the things we've already talked about. So it kind of combines a lot of stuff that we've done. So we'll kind of see it again, and hopefully that'll reinforce some of the ideas, including using patterns, recursion, all that kind of stuff. At some point, I don't know if I'll get there today, but I'll show you how to implement a binary search tree. Not a balanced tree, just a normal binary search tree in Haskell. And it's literally, so using user-defined types, it literally takes up like a page to implement the whole thing. So it's kind of cool to kind of see it all come together in that way. All right. I think that'll be next time though. So you can user-define your own types, data types in Haskell, and to do that, you use a new keyword called data. And so this gets people hung up because there's also another keyword called type in Haskell. And so I'll talk about both of them. So for now, you just have to remember, if I wanted to create a user-defined data type, I have to use the data keyword. And Haskell will yell at you if you do it incorrectly. You just have to remember there's data and then there's the type keyword. So what I'm going to do first is I'm going to define a really simple data type, user-defined data type for storing information about books. So it's really like a record, like a struct kind of in Haskell. So so I'm going to give the definition, and then I'm going to kind of break it down and talk about some terminology, so what each of the parts are about. All right, so the actual user-defined data type, the syntax would be the following. So I use the data keyword, and then I specify the name of the type. So here it's, I'm going to call it book type. Okay, and then so basically I'm saying that I'm creating a new user-defined type, and the name of it is book type. And then I basically specify what the structure of a book type is. So in this case, I'm going to say a book consists of an int, a string, I'll say what that is in a sec, and a list of strings. Let me actually move this down a little bit. And then I'm going to do one additional syntax thing, and I'll talk about what this is in a second. We'll get there in a second. So I say deriving show. Actually, does anyone remember what show is? Can somebody tell me what show is as a thing? Like, what kind of thing is show in Haskell?
It's a type class of printable type.
That's right. So show is a type class. And so here I'm basically connecting up the show type class to this type I'm implementing. So I'll talk about that in a second. So now I'm going to kind of define kind of break this into parts. So each part has a specific name in Haskell, so you have to know what the names are. Okay, so the first thing, just starting at the beginning, so we already said data is a keyword, it's a reserved word in Haskell. So the next thing is this book type thing. So this is what's called a type constructor. And it's, so one thing is all types in Haskell always start with a capital letter. Okay, types are always capitalized. Which is kind of, whoops, too many I's, capitalized. Which is kind of nice because then it makes it really easy to figure out like what's a type and what's not a type. Okay, so that's why, so the type constructor book type starts with the capital letter B. So here you can think of this like, it's basically like the type name. It's the name of the type. But it's called a type constructor. Okay, so then on the right-hand side, that's everything on the left-hand side of the equals. Everything on the right-hand side, the very first thing is this book thing. So it's capitalized, so it looks like a type. What it's called in Haskell, it's kind of different, I guess, than a type. It's what's called a value constructor. So, or sometimes a data constructor. And so the basic idea is that the book type, the thing on the left-hand side, that's the name of the type. To create an instance of the type, we use the value constructor. So we use this to actually create an instance, and then the type is the name of what we, or the type of the thing that gets created is a book type. So we use book as a way to create an instance, and then the type of the thing that we create is, in this case, book type. So I'll kind of show a little bit more of that here in a second, after we get through some of the terminology. So the int, string, and list of string, so those things are what are called fields. And actually, it's a lot like a record or struct type. So you have the name of the type, and then you have the attributes in the struct. So the attributes are often called fields. And so in Haskell, they're also called fields. And so basically, in this case, we can think of a book as having three fields. So it has an int, it has a string, and it has a list of string. For us, we're going to use the int as like the book identifier, it's like the ISBN or something. The string is going to be the name or the title of the book, and then the list of string is a list of the authors of the book. So string, we'll talk more about string, but string is just another name for a list of char. So it's just a shorthand for a list of characters. So just what you would normally think of as a string in Haskell. Okay, and then the last piece, this deriving show, is kind of a trick, I guess, in Haskell when you're doing user-defined types, that some type classes will automatically basically implement the functions associated with the type class. So show is one of those, and in the case of show, basically it allows us to print out a book, okay, to show an actual book instance of the book type, a value of the book type. And so show just has one function called show, and all it does is basically print, it's going to print book and then the ID the title, and the list of authors. It's just going to print the value constructor followed by the fields, basically. Another one that you can provide in deriving is EQ, and then you can do basically comparisons based on the values of the fields between two objects of a particular type. Here we didn't give it, but we could have. Maybe I should do this in, I hate to even try. I did figure out how to, to mute this. Why not? So let's do this in, where is it? Oh, it's not there. Let's try to do this from the terminal. For fun, and I have to just change this real quick. Can people see that okay? I have battery. So I'll connect to Ada. And we'll create a file called books. We'll use Emacs. So I'll just type this out. So it's data book type equals book int string list of string, and then deriving the show class. And then I'll save this, and then open up GHCI, and now I'm going to load the books file. Okay, so it was okay with my type definition. Okay, so then now what I'd like to do is I'm going to create an instance of a book type. So actually, if I come back over here, if I can do this. The way this works is, so for example, if we're sitting in GHCI, then to create a book, I would use the value constructor. Okay, and let's say the ID for the book that we're going to create is book 23, and the title is going to be my book, and there's only one author, Alice. Okay, so this is basically the syntax that we would use to create a book object. So here, whoops, I would type book. I give the int, which for us is the identifier. I give the title, and then I give the author. Okay, and then if I hit enter, it works, and it just prints out the instance that I created. So here, we're using the value constructor book to create a new value, which is of type book type. So, and the reason why it printed out was because I had that deriving show. So actually, if I, well, I'll just leave it there. If I were to take that off and I typed book 23, my book, I did the same thing, it would complain at me and it would say doesn't implement show. Okay, so I'm gonna save this book because we're gonna use it here. Some more in a variable or in a binding B1. So now if I ask for B1, it just prints out what B1 is. So now what I'd really like to know is what is B1's type? So here I said let B1 equal book. Whoops. Alice. And now I want to know what is the type of B1. So it's what Haskell is going to tell me is that B1 has a type, but somebody tell me what the type is that's going to be output. What is the type of B1?
Book type.
Book type. So if I come over here and I enter, it says it's a book type. Okay. Because that's the type constructor, or that's the type name. Okay, so what on earth though is this book thing? So if I want to know, again, book is a value constructor. Okay, book is a value constructor. In like in C++ and Java, when we think of a constructor, it's like a function, right? You call a function, you pass in some stuff, and what does it give you back? Like if I create a class, I have a constructor, I call the instructor, what do I get back after the constructor executes?
An instance of the class.
An instance of the class. That's what the constructor does, is it creates the instance. So here I have a constructor. It's a value, call it value constructor. So what is the type, what kind of a thing do you think book is as a value constructor? Based on what I just said.
Would it be int, string, and then list of string? Like arrows?
Right, so what is that? That would be what kind of a thing?
Function. Would that be a book type?
Go ahead.
Would that be a book type? Or that's pretty obvious, but
Well, so yeah, so when I say book, when I do book 23, my book, list of Alice, what I'm doing is I'm basically like passing those fields in and creating an instance of a book type. So I'm creating a value whose type is book type. So book as a constructor sets some fields and then returns basically a instance or a value of the type. Okay, so what kind of a thing is book? Is it like its own thing, or is it a function, or is it a variable or simple value, or what is it, do you think? Given what we know about like Haskell, what do you think book? It's a function. Okay, so a book is just everything's a function in Haskell. Okay, so back in the interpreter, if I ask for the type of book, then it's going to tell me that book is a function. It takes 3 arguments, and then it returns a value. So it says that book is really just a regular old function. At least it seems that way. It takes an int, it takes a string, and it takes a list of string, which happen to be the fields, and then it returns a value, which is a book type value. So the result is an instance of book type. Any questions about that? So just to summarize, so if I come back, make this side a little bit, there we go. Make this side a little bit bigger. So far, we've seen the syntax for defining user-defined types. We saw this data keyword. Data takes a type name, so like book type, that's called a type constructor. And then the right-hand side, we define a constructor. So that has a name. It's really just a function that takes some arguments and then builds and returns a value of the type. So in our case, book takes the 3 fields and then it returns a book type value. What's different, I think, with Haskell versus maybe other approaches is there's no state that's being managed other than just kind of the book holding together the fields. So like the whole thing together, this notion of a book constructor with the 3 fields, that's actually all there is to it. Okay, so we'll talk a little bit more about that as we go. So one thing, just in terms of sort of types in Haskell, and many languages are actually this way, is that Haskell data types are what are called nominal types. And what all this means is that the name of the type is what distinguishes different structures. So I could have 2 different like structs or structures with the same fields, the same 3 fields, but if they have a different name for the constructors, then they're fundamentally different types. They're different things, and they can't be compared. They don't have the same type, even though they're just carriers for like 3 different values. So the basic idea of a nominal type is that different names means different types. This turns out this is now true in most languages today, where, so for example, in C or C++, I can define a struct type, or like in C++, I can define a class type. The class might have, so 2 different classes, that is 2 classes with a different name, might have the same exact member variables and the same exact functions, but because they have different names, they're considered to be completely different types. So if I create an instance of one, it's incompatible with an instance of another, even though they're like identical in everything except for the name. So just as an example of this, if I go back to Haskell, oops. So if I go back to the book definition, so here I'm going to create another type called magazine type, and it's going to have a different constructor. Make that bigger. So in this case, The magazine type is a different type name, different type constructor, and a different value constructor. But they have the same exact fields. So in this case, the two values, even though they might be identical, if I create a magazine value versus a book value, even though they could be identical, they're fundamentally different. Yes, so somebody asks, an instance of a book type is the value constructor applied to the field. Effectively, yes, it's the value constructor plus the values for the fields. So if I go back to GHCI and I load this again, oh, whoops. We'll go book one, my book, Alice, and we'll say M1 is magazine one, and we'll call it my book, and it's also Alice. So B1 is a book, M1 is a magazine, and these two things are completely different. They serve as different, fundamentally different values, even though the fields are identical. If I come back here, so like I said before, we can also derive from EQ. So I'll do that for both of the types. I'm going to start up JCI again. I'll load books again. So in this case, so I'm going to create a book. I'm getting sloppier. Which was written by Alice. I'm forgetting the ID. Okay, I'll do another one, which is, again, a book with the same title and the same author. I'll do another one, which in this case has a different book ID, but the same for everything else. And then I'll create a magazine, which is the same as B1 and B2, but with a different type constructor. So because I implemented EQ, I can check, for example, equality. I can check if B1 is the same as itself, basically, in which case it is. I can also check if B1 and B2 are the same, which they are because they represent the same value. So again, this goes back to what Ewan was asking, that in Haskell, it's a little bit different in the sense that there's no like object identifiers. These are really just values, and the value is the value constructor plus the fields. And so in this case, B1 and B2 are the same because they have the same value constructor and they have all the same fields. Whereas B1 and B3 are different because they differ in the book number. And then if I try to check if M1, for example, is the same as B1, well, even though they have the exact same fields, they're completely incompatible. So what do you think is going to happen in this case in Haskell?
Error?
So what are some, error. Okay, so it could result in an error. It could say false because they're not the same. That would be, if it said,
just
it
a
could say
possibility.
true. Yes, that's good. So it could say true, and it would say true because they would have the same fields, for example. Like it's just a container for three values, book and so M1 and B1, they contain the same values, so they're the same. So we return true. It might return false because books are different than magazines, or it could be an error. So the first two cases, true or false, that would be something that happens like at runtime, right? It's going to check, are they equal? Maybe in the false case, they're not equal because they have different constructors, value constructors. In the case of an error, I would argue that the error would happen because of a type error. And what we do know about Haskell is it's very picky about types. So when I say equal, equal, it's going to it is type checked. So just like in MyPL, equal, equal only works, or comparison only works, if the left and the right-hand side have the same type. So in this case, the error would be, as a result, I would argue, because they have a different type, because they're fundamentally different, even though they have all the same values. And so that's what happens in this case. And you can see that it complains because it's saying that magazine type and book type, which are the two types, are different. And so they don't match. They're incompatible at this point. Okay, so I don't know, that was kind of a long explanation, but hopefully that makes sense. If we come back, so actually I'm going to go back here. My handwriting will get better after I do this, hopefully. So another aspect of types in Haskell is that it turns out that the type constructors and the value constructors come from independent namespaces. So the type and the value constructors, or the names that are used for those, are independent. And so what this means is the way that we laid this out, where we gave a different name for the type constructor versus the value constructor. So this we gave book type, and this we gave book. It turns out we could actually, those don't have to be different. So we could have just said book here instead of the full book type, because Haskell's still able to differentiate them because types have a different namespace than the value constructors. And so it turns out that the convention in Haskell is really to name, like in this kind of a situation, would be to name these the same. We'll see later that it makes more sense to actually have a type name and then to have a different name for a value constructor. But in this kind of setup, it's really the conventions to use the same name. So if we come back down, that's going to look something like the following. So we'd say data book equals book int string list of string, and then the deriving, whatever we want to derive. And we could do the same with magazine if we wanted to. I think I'll leave this there. There's a little bit of detail in the notes about so this idea of deriving from a type class. Actually, maybe we'll talk about it. It's somewhat interesting. So actually, if I come back, the last thing we did in the example was I did deriving show and EQ. Okay, and the effect of this was that by default, EQ is going to look at the fields. So if I have two different books, B1 and B2, and I try to compare those, it's going to return true if all of the fields have the same values. So if B1's int is the same as B2's int, B1 string is the same as B2 string, etc. So this is using the default implementation of the EQ function applied to user-defined types. So it just does a comparison on the fields. So it's also possible to kind of independently implement different type classes for your user-defined types. So in this case, if we left off the EQ part, we're going to leave that off, and we're going to define our own version of equality checking. And so the way that this would work is separately, we're going to say that book is an instance of EQ, and in order for that to work, we have to specify the, or as part of that, we're going to give our own function definition for equality checking. So here we're saying that book is an instance of EQ, okay, where we're going to define the following functions. So we're going to define equality checking. And it turns out that with user-defined types, we can do pattern matching. So we'll talk a little bit more about this and how it works in a bit, but I'm just going to show you an example. So the first argument, we're expecting a book value, and it's going to have an identifier ID1, and then we don't really care what the other two values are. So the way that we're going to define equality in this case is instead of checking every single field, we're just going to check the book ID. And if two books have the same identifier, the same number, then we're going to consider them the same book. So that's how we're changing the definition. So this would be the first argument. And then the second argument, we also expect a book, and its identifier is going to be ID2, and we don't really care what the rest is. And the way we're going to define equality is we're just going to return true if the two identifiers are the same. And that's actually all we would need to do in this case for implementing the EQ class. And in this particular case, the other operation that's supported in EQ is not equals, but we can just use the default implementation of not equals, which is to call equals. So in this example, again, this expression uses pattern matching. And we're matching, in this case, on a book value because of the, and in this particular case, this is the book constructor. So it's the book constructor, sorry, the value constructor. Basically tells us what kind of value we're matching on, and then binding the ID part of the book value, as opposed to the title or the authors. Are there any questions about this? We'll talk more about this idea of pattern matching here in a bit. This is maybe more foreshadowing for pattern matching over user-defined types. Okay. So what we're really doing at this here is just saying that book implements the EQ interface, and we're giving within that the definition of the EQ functions. So it's actually quite straightforward. Okay, so we talked about this data type now, the data keyword, and in the beginning I said it gets confusing because there's also something called type, which is another way to specify types in Haskell. So I'm just going to go over that real quick. This notion of the type keyword. So the idea of the type keyword is that you use it basically to give a different name for an existing type. It's actually very similar to like typedef in C and C++. So the idea is you can give a new name for an existing type. So sometimes this is really helpful when you're defining a user-defined type. So in our book example, for example, we have just the fields without any kind of name associated with them. So one way to help make it more explicit what the fields are for, we can use type synonyms to do that. So just as an example, we could say that ID, so we're just creating that on our own, we just made that up. ID is a synonym for int. And then we can say that title is also a synonym for a string. And then authors is a synonym for list of strings. And so we're just giving a different name for individual types. You can think of it like typedef. Oops. In C and C++. It's very, very similar to that. So then we can use these when we define our user-defined data types. So in this case, we would say something like book has an ID, a title, and a list and authors, and then deriving whatever. Any questions about that?
Is there any way you can create the type synonyms in the value constructor or in the data definition?
Yeah, so this is not necessarily the best way to name that attribute or to name the fields. There's another way to do that where we can explicitly give like attribute names. So that's usually a better approach than this. And I think I don't know if I have that in the notes. I think I kind of skip over that just because it's a detail, so that we can get quicker to defining functions and kind of using some of this stuff. I think it is a little bit later in the notes I'll show this. So right now, these type synonyms are really just kind of poor man versions of that, I would say, where you can actually explicitly give field names. So we'll talk about that later. So just moving forward, and one of the reasons why I want to talk about type is that it's confusing for people. So when you start doing this stuff, your natural inclination is to use type instead of this data keyword. And so if you do that, it's good to know why that doesn't work, because it can be frustrating. So you just have to remember type is like typedef. So it creates type synonyms, whereas data is actually the thing that it helps you create user-defined types. So one thing about types, type synonyms is that they're the opposite of nominal. So a type, whoops. Sometimes people call these structural as opposed to nominal. So in particular, an int and an ID are basically, we're just creating a new name for an int. So given two int values, so like the value 42, that's both an int, right? We already know that. And once we've done the type synonym, the value 42 has the same, its structure is also, because of the synonym, an ID. So the value is sort of, so two different instances, an instance of an int and an instance of an ID. If they're the same value, they're an instance of both types. Right? I don't know how, if it's an int, it's also an ID. If it's an ID, it's also an int. It's based on the structure, not the name. Okay, so as another example, actually we kind of introduced this notion of a string. And it turns out that in Haskell, in the prelude, there's a definition, a type definition, which is just to have string be another name for list of char. So that's how string came about. The other thing that you can use types for, which is sometimes handy, is if you don't want to create a user-defined type, but you want to be able to use some existing structure like a tuple and name that as a type. So for example, in our whole book example, really for us, a book is just a 3-tuple. It has an identifier, has a title, and has a list of authors. So another way we could do this would be to literally just define it as a 3-tuple and name it. So we would say something like book record is a 3-tuple that has an ID, a title, and then authors. And so now I can use this book record as the name of a 3-tuple. Okay, so we have just a few more minutes. So I'll just start talking about a few more features of user-defined types, and then we'll pick the rest up later. So one thing is that a value constructor can actually have 0 or more fields. So we've seen the more fields, but we haven't seen an example where there's just there's no fields. So I was going to give one example of this. Actually, let me do this. Oh, sorry. I mean, I have to be careful. So value constructors. Can have 0 or more fields. So, excuse me. So as an example, we could have something like define a type called red color, and it's only So value is a value constructor red. And then we might say it's deriving show and EQ. So really all we're doing here is we're using a value constructor to represent a unique value that doesn't have any additional fields to it. So the other thing is you can have multiple value constructors for a given data type. So for example, let's say we wanted to define a type that represents the colors red, green, or blue. So the three values of our type are red, green, or blue. So we can do that using three different value constructors with no fields. So we would say red, green, whoop, a red, green, blue type. We'll say color. And then we have three different constructors. So we can, we'll use the example from before, red. So that's one RGB color, red. Okay, another one is green. That's another RGB color. Or the other one is blue. So just like with grammars that we talked about a long time ago, so this symbol, the bar, basically just stands for or. So in other words, if you read it from left to right, a red, green, blue color is either the red value, the green value, or the blue value. When I'm using this in Haskell, I can just type like red, and then it'll just, because we derive show, it'll just say red. Or I can say something like let color 1 equal blue, and let color 2 equal red. And then I can, because I'm deriving from EQ, I can say is C1 equal to C2. In this case, it would say false, because they're different values. They're different value constructors. If I said maybe C1 not equal to C3, C2, in this case it would return true, because they're different values. We've actually already been using a type that's defined exactly this way, and we were calling it a primitive type, one of the primitive types. Does anybody know which one we're talking about? What primitive type have we already seen that we can define this way?
Is it Boolean?
Bool. In fact, bool is not a built-in type in Haskell at all. So bool, the way bool is defined within the prelude, within Haskell itself, it's defined as a user-defined type. So it's defined exactly like this: true or false, and then the deriving show and EQ. So again, it works exactly the same as what we were just talking about with RGB color. So just to kind of go back over what we've seen so far. So we've looked at just the basic use of data, the data keyword, which is for creating user-defined data types. And a user-defined data type has a type name or a type constructor, and then it has one or more value constructors. And a value constructor has a name and then 0 or more fields. And so we looked at how to create values using the value constructor. And now we've looked at these cases where you have types that have multiple value constructors. And so next time we'll kind of go further. We'll talk more about pattern matching over user-defined types, and then kind of combine all this stuff and look at how to do like linked lists and binary search trees using the same, just using the data constructors or the user-defined data types. And I'll stick around for a few minutes if folks do have questions.
Thank you.
Yeah.
Hi, this isn't a question related to this class, but I need to meet before registration. I was wondering when a good time to do that would be.
Oh, okay. Tomorrow, I have office hours from 1 to 2, and then I do have other times tomorrow. So if there's some times, usually like from 11 on, I'm available. Sometimes at noon I don't, but tomorrow I think I have my noon hour open. So basically from 11 on tomorrow, I'm available.
Okay, noon would probably work best for me tomorrow. Would that be okay?
Okay. Yeah. So just if you could just log into the same Zoom ID.
Okay.
I'll be there.
All right, sounds good. Thanks.
Okay. Yeah.
But